Thank you. And thanks everyone. Yeah, we'll use it for the. So wow, thanks. That was a long day, but it's ongoing. Yeah, we have now the last poster session. Will begin in about 10 minutes, and then outside, yeah, you can also have home food while talking with the posters presenters. So the last group of posters, we are looking for about 14 out of you, yeah. So please, if you can line up here, each one of you will have 40 seconds or so to quickly intrigue us. So how do we do it? Yeah, so trying to find the. Oh, yeah. And let's. So let me give. Oh, yeah, we'll see each time which one. Yeah. So. Oops. Who's first one? You don't know. So. Oh yeah. Oh, I thought we changed the order, but anyway, okay. So first one, Vanessa, please. Please.
Thank you. Hello, my name is Vanessa Laya. I'm a PhD student at the University of Sydney. My research is mostly on simulating chemical dynamics using analog quantum simulators. So we have recently mapped the molecular Hamiltonian into an analog simulator using the electronic and the molecular degrees of freedom. We are now extending this closed system simulation into an open system simulation where we have included control dissipation and the native dissipation of the simulators such that we can simulate a molecular system, including the environment. So if you are interested, please come see my poster and talk to me. I'll be happy to discuss it.
Grace, please.
Hello, I'm Grace from Harvard University. I work in John Doyle's group, and we work on laser cooling of molecules. So many of you might be familiar that it is possible to laser cool atoms with like 1 or 2 lasers. Well, I'm here to tell you that it's also possible to do it for molecules as long as you have enough lasers like that. And if you come to my poster, I'll show you that not only can we laser cool them, we can also trap them in a MOT, and we can load them into conservative traps, and we can load them into arrays of rearrangeable optical tweezers. And the reason we're doing this is not because we like lasers. It's because molecules are actually very promising platforms for quantum information, quantum simulation, and precision measurement of fundamental science. Thank you.
Thank you very much. Robin, please.
Hi, my name is Robin Learn. I'm a PhD student in Joseph Tywison's group here at U of T. And in our experiment, we realized the single band Fermi-Hubbard model by loading a spin mixture of 2 spins of an ultra-cooled Fermi gas into a 3D optical lattice. So in this poster, I'll be talking about how we drive a neutral mass current in the lattice. And we image those dynamics by taking in situ density distributions, making pretty pictures like this. And what we're interested in looking at is seeing how the interactions between these 2 spin states dissipates the current and changes this current. Yeah.
Thank you. Please.
Hi, everyone. My name is Vivek. I'm from the and my research pertains to exploring 22 nanometer FDSOI technology, which is a production CMOS technology in our everyday phones, as an avenue for doing semiconductor spin qubits, quantum computation. So we have scaled sort of realistic devices in our atomistic simulator and explore multiple backgate designs And back gates are usually used to tune the barrier between two adjacent quantum dots, which will house your spin qubits. And this tunability can help you with transport, can help you with coupling 2-qubit gates, etc. So there's a lot of parasitic barriers that we have to deal with, and also live within the bounds of realistic manufacturability limits. So it's a very fun engineering problem, and I'll be right by the piano with my poster.
In our work, we take a rather unusual approach to the problem of quantum Maxwell's demon, where we use reinforcement learning to solve the problem. It allows us to achieve two tasks. First of all, it allows us to solve problems that are not solvable with conventional non-AI techniques. And second, it gives nice interpretation to the neural networks themselves we train, because effectively neural network becomes the Maxwell's demon in our problem.
Okay, so my name is Matt. I work here at U of T with Vera and Nathan Reed. Yeah, so at least we got that. Yeah, so if you got one takeaway from this afternoon, it's that Hamiltonian simulation is a hard problem. If you want to further complicate that and include dissipation, do Lindblad dynamics, I don't think people would argue with me with saying that's a harder problem. And state-of-the-art algorithms to solve that problem achieve good asymptotic complexity, but they're very, very complicated algorithms. So we take a different approach in that we use a tool called repeat interactions to essentially embed non-unitary dynamics in a larger unitary Hilbert space. And through this iterative prepare and trace out strategy, we can use those state-of-the-art Hamiltonian simulation algorithms we like to get some pretty good asymptotic complexity. Again, if you're paying attention to some earlier talks, it's pretty similar to the best we can do, except for this sort of new parameter, which is sort of this convergence thing, which you'll have to come to my poster to find out more about. But yeah, thanks.
Hi, everyone. I'm a master's student in Lee Chan's group here at U of T. So we're dealing with generating entanglement witnesses with machine learning. So it's like entanglement detection in systems of qubits. This was done originally a couple of years ago, presented here at this conference. A problem comes up when you try to do this with larger systems. You have this sort of curse of dimensionality. So you have, if you just randomly sample training data, the size explodes, it becomes infeasible. So we found a way to sample only very specific training states and do some additional optimization to ensure the highest noise tolerance and perfect accuracy. So for more information, just yeah, check out my poster. Thank you.
Hello, everyone. I'm not Andy. My name is Jackson. We are in the same research group, and I am here in his stead. So today, I'm presenting a project that we've done where in our group, we use a special kind of fiber in order to generate entangled photons using SPDC. Typically, in the past, we've used a titanium sapphire laser in order to pump this process in a pulsed manner. However, this is quite an expensive, complicated, but beautiful system. However, in this work, we've replaced the TISAF with a custom pulse diode system, generating an entangled state of high quality, but at a lower cost. Thank you.
Oh, my name is Michael, and I will talk about some of our calculations on high gain squeezing in these kind of dual ring photonic molecules. The idea being that we want to generate degenerate squeezed light in a single ring resonance. like the red process shown in that diagram on the bottom left. But of course, when we have a dual pumping scheme, we have a bunch of other Fourier mixing processes given by those dashed lines that can destroy a lot of the squeezing that we want. And so instead, we consider this kind of two-ring photonic molecule where we can selectively split resonances that we don't want and suppress these parasitic processes to try and isolate for just a single dual pump process. Thank you.
Hello, everyone. My name is Ray Jie. I'm a PhD student at Ephraim Steinberg's group here at the University of Toronto. Consider a scenario that someone is giving you a classical bit. You can make any number of copies of this classical bit without gaining information. But this is not true for qubits because you cannot clone qubits. If you have more copies of the same qubit, you're gaining information. What I'm going to show you in my poster presentation is our experimental results on compressing arbitrarily large number of unknown qubits into a fewer set of qubits and while preserving all the information. Thanks a lot.
Hi everyone, I'm Batuan from Ephraim Steinberg's group in U of T. The experiment I present in my poster is about an imaging problem where we want to estimate the separation and the relative intensity of 2 point sources. So normally, for example, if you want to image stars, you point your telescope, put a camera, measure the intensity profile. The problem with that method is when the sources are too close, then your uncertainties of the parameters blow up. When you use the tools of quantum metrology and find the quantum bonds, it turns out there's a better way to measure these light sources. And that's the Hermite-Gauss basis, so the mode projection, or you can roughly approximate it with linear optic systems. So if you want to find out how well we did, you can find my poster behind the stairs.
Hi, everyone. My name is Yu Xuan. I'm a postdoc here at localized CQIQC, co-hosted by Youngbai Kim and Juan Calasquia. So as Matthew previously pointed out, that Hamiltonian simulation is already hard, and we're gonna, in this work, make it harder by considering non-Hermitian Hamiltonians. So you may ask that why do we consider non-Hermitian Hamiltonians? Don't we learn from our undergrad quantum mechanics class that Hamiltonians should always be Hermitian? Well, it turns out that if you consider open quantum systems in the presence of measurement and post-selection, the non-hermiticity pops up naturally. And this post-selection nature actually makes the problem a lot harder because you need to take extra shots in actual experiments. And in this work, we made use of variational quantum compilation method and show that for certain quantum systems and under certain non-Hermitian Hamiltonian dynamics, you can actually compress the circuit. And in the end, we observed a supersonic mode on Quantinuum's 20 qubit trap-time quantum computer. And I've only told you half of the story. And if you're curious about the rest of the story, come and talk to me at the poster session. Thank you.
Yeah, hi, my name is Artyom. I'm a PhD student at Quantum Simulation Lab at the Institute for Quantum Computing. And here is our research group. So there are many of us, and here is our quantum simulator right here. And we are interested in asking such questions as how do we realize perfect state transport, spin transport in a like 1D array of spins. And then another question is how can we model spin motion entanglement in these arrays efficiently? How can we reconfigure array of quantum particles? And another question of interest is how do we design robust and high fidelity control pulses? So, and if any of that interests for you, so please stop by, and also have a website, quantumsimulators.com. And also for a promotion, so my supervisor is going to give a talk tomorrow after lunch, please, if you want to learn more. Yeah, thank you.
Thank you very much. Yeah, so please, outside you will have the posters and additional food, and please come tomorrow for the last day. And I also just wanted to mention that the fields are super fast, and already they've been uploading recordings of the first 2 or 3 days already Yeah, they are about, within one day they are uploaded. So if you go to the program online, within the fields and click on the talks, you already have the recordings there. Thank you.